Hi guys, welcome back to this channel and nice to see everyone again. And for today's video, we'll talk about topic 9.2 where we will discuss factors affecting the reaction rate. So we'll look at the factors that can increase the reaction rate and also decrease the reaction rate. Along the way, we will explain the effect of each factor, and we have 5 factors to discuss in this video. So the factor affecting the rate of reaction, the first one can be concentration. But bear that in mind, concentration can only use when it's applied to gas or when it's applied to aqueous only. When you have a solid liquid, you cannot talk about the factor concentration. The next, we have pressure and volume. Pressure and volume can only be discussed when you are talking about gases, because only gases we can talk about pressure. Okay? The next factor that I have is temperature. Another factor that we can discuss is catalyst. The last but not least, we have particle size. And bear that in mind, particle size can only be used when the reactant is solid. So you only can talk about the particle size when you involve solid. So be careful with the restriction of certain factor. We have 3 factors that are restricted to certain physical phases. The first factors that I have is concentration. Bear that in mind, concentration we have agreed just now can only be used for gases and also aqueous. We cannot talk about concentration when it's solid and liquid, because for solid and liquid, the concentration are constant. Remember that. I have 2 conditions over here. Pretty obvious is I have a lower concentration over here. You can see why is that a lower concentration? Because the number of particles is less. Alright, the number of particles that you have over here is less. And obviously over here is higher concentration. But if you look at the 2 pictures, there is one similarity. Alright, both of the container size are the same. So, concentration can only be discussed when you are in the fixed or when you are in the same volume of container. Alright? So when the container size is the same or fixed, then only you can change the concentration. And if you look at the lower concentration, you have less number of particles. When you have less number of particles over here, what happened? The collision will be less between the particles. Alright, the collision between the particles to produce product will be less. For the reactant to become product, the reactant need to collide with each other. You need to have a collision, then only you can form product. Then only your reaction will happen. So when you have a less number of particles over here, collision will decrease. When collision decrease, the effective collision will also decrease. Effective collision is the collision that will change your reactant to product. So when the collision decrease, effective collision decrease, therefore, your product will be decreased. As a result, your rate of reaction will decrease. That is what happens when you have a lower concentration. But what will happen when you have a higher concentration? Look at it. When you have a higher concentration, you have a lot more particles. Can you see that? You have a lot more particles, but you are sitting in the same container. So in the same size of container, but you have more particles. The number of reacting particles is higher. In the same size of container, the container is the same size, but the number of reacting particles increase. What happened to the collision? So obviously, you can see that the reacting particles can collide more over here because they are closer to each other, right? So collision increase. When collision increase, automatically your effective collision will increase. When the effective collision increase, obviously, more reactant can change into product. When more reactant can change into product, that is the reason why the rate will increase. So as a conclusion, when concentration increase, the rate of reaction will increase. Let's look at the summary of the explanation for the factor of concentration. When the concentration of reactant increase, more reactant particles in the same volume. Bear that in mind, you must have the word same volume. More reactant particles in the same volume. Therefore, higher collision between the reacting particles. Number of effective collision increases. As a result, rate of reaction increases. So when the concentration increases, the rate of reaction also increases. The second factor that we will discuss is particle size. Bear that in mind, particle size only apply when it's a solid. And the good friend of particle size is the word contact surface area. And a kind reminder over here, the relationship between contact surface area and particle size are inversely proportional. It means when my particle size increase bigger, it means that my contact surface area decrease. Remember that. Alright, the particle size and the contact surface area are inversely proportional. I have two conditions over here. One, you have a very large particle size. Can you see? This is my whole solid. One big block of the solid. So the particle size is very big over here. The particle size of who? The particle size of the reactant is very large over here. Well, in this case, you can see that from a big block, I cut it into smaller block. So I have a smaller block over here. Alright, I have a lot of smaller block over here. It means that my particle size of the reactant decrease. Alright, the particle size of the reactant decrease. And as we agreed, the particle size is inversely proportional with the contact surface area. Let's see. The particle size over here is very big. And the contact surface area is only this side. Alright, you only have this area of contact surface area. Compare over the particle size when it's smaller. When the particle size is smaller, you have a lot more contact surface area because all this area can be formed intermolecular forces. So all this is your contact surface area. And comparable wise, if you can compare in the diagram, you can see obviously when the particle size of the reactant is smaller, the contact surface area increases. Alright? And when the contact surface area increases, back to the collision, because this is your reactant. This is all your reactant. You want to change your reactant to product, you need to have collision and also effective collision. So when the contact surface area is larger, obviously the collision will increase. When the collision increase, we still back to the effective collision. Effective collision means the collision that can change your reactant to product. So when your collision increase, automatically your effective collision increase. As a result, more reactant can change into product and rate of the reaction increase. Can you see that? Can you see the relationship over here? So particle size of the solid is very, very important. Okay? I can give you a very simple example over here. You have a big block of sugar. And also you have small bits of sugar. Which one is easier to dissolve in water? Obviously, the small bits of sugar is easier to dissolve in the water. Why? Because the particle size is smaller. Therefore, contact surface area is larger. A lot of the contact surface area of the sugar can react with the water and dissolve easier. That's why a bigger size sugar is harder to dissolve and it's easier to dissolve a smaller size sugar. Make sense? Alright. Let's look at the proper explanation of it. When the particle size of the reactant decreases, the contact surface of the reactant increases. The higher collision between the reacting particles, the number of effective collision increases. As a result, rate of reaction increases. So bear that in mind, if you want the rate of reaction to increase, your particle size must decrease. So the particle size need to decrease so that the rate of reaction will increase. Because the good friend of particle size that you must mention is contact surface area. Simple? Let's move on to the third factor. The third factor over here is pressure. As we agreed just now, pressure can only be applied when it's a gas. So be careful, make sure your reactant right now involves gas, then only you can put in the factor pressure. And pressure comes with a very good friend, which is volume. Whenever you discuss about pressure, you always discuss about volume. Vice versa, when you discuss about volume, you always discuss about pressure. Same thing, I have two conditions over here. If you look at it, the beaker on the left-hand side have a lower pressure. The pressure over here is lower. Alright, that's why you can see that the pump is still at very high. And over here, the pressure is extremely high. The pressure is very strong, so we push the pump all the way down. And you can see your pump is down here. And if you calculate the number of particles that I have, the number of particles are the same. The number of red dot over here, the number of reacting particles are the same if you calculate both left and right. Okay? That means they are having the same amount of concentration, but we are only changing the pressure and volume. As you can see over here, the pressure and volume are also inversely proportional. When the pressure is very high, automatically the volume will be very low. As you can see over here on the left-hand side of the beaker, my pressure is extremely low. Alright, very low pressure. Automatically, the volume is extremely high. Can you see? This is the area of my particle located. Vice versa, if my pressure is very high, I press it very down. Alright, I press it very strong. Automatically, the volume will decrease. Can you see over here? Your reacting particles only sitting in this small area. So what happens when you have the same number of reacting particles but different pressure? Volume changing. When volume changing, the distance between the particles also changing. You can see on the left-hand side beaker, the distance between each of the reacting particles are very far from each other. Can you see that? The distance between the particles are very far from each other. Vice versa, look at when the pressure is higher. When the pressure is very high, you press the pump down, you force all your reacting particles into a smaller volume. What happens when they're sitting in a smaller volume? Look at their distance. Look at the distance between the reacting particles. What happened to the distance between the reacting particles? The reacting particles will become closer to each other. So comparable, your left and right over here, which one will give you more collision? Which one do you think will give you more collision? Which condition that the reacting particle will collide more? Obviously, the one that's closer. So obviously over here, the collision increase. So we are talking about the same thing, guys. Alright, the collision increase. Then, what happened? Effective collision increase. When the effective collision increase, the rate of the reaction again increase. So the last 3 points is pretty much similar. Alright, at the end of the day, we want to change the reactant to become product. So to change the reactant to become product, the reactant must collide and the reactant must have effective collision. Then only the reactant will change to product and the rate become higher. Okay, so it's similar. But in mind, pressure always talk about volume. Okay, when the pressure increases, volume decrease. Reacting particle will be closer to each other. Higher collision between the reacting gas particles. Number of effective collision increases. As a result, your rate of reaction increases. Simple. Just a kind reminder over here because your pressure and volume only involve gas. So if you look at my explanation is more details. I mentioned gas molecule, reactant, gas particles because your pressure and volume only apply to gas. And for the rate of reaction increase, if I want to increase the rate of reaction, your pressure must increase and your volume will automatically decrease. Simple. Let's look at the next factor, temperature. Temperature, obviously we have one cold and hot temperature. So if you look at it, again, the number of particles is the same. Left in the cold, you have 6 particles. Right in the hot, you also have 6 particles. But what happens when it's a cold and hot? Obviously, if you can see over here, alright, the movement of your particles become faster. Particles move very fast means what? Means that the kinetic energy of the particle is very high. So the kinetic energy will increase when the temperature increase. Look at your diagram. When it's cold and when it's hot, which one gives you more collision? You can see it very clearly over here. Obviously, the one in the hot will give you more collision. Higher collision. And obviously, guys, the same thing. When higher collision, higher effective collision. When higher effective collision over here, obviously, rate increase. So rate will increase when the temperature over here is higher. Because the particle can move faster, automatically they will collide even more. So you can see over here, the temperature, we will talk about the factor kinetic energy. See that? So let's look at your explanation. And obviously, vice versa, guys. If you look at the temperature is cold, what happens when the temperature is cold? Temperature decrease. When the temperature decrease, the particle obviously moves slower. When the particle moves slower, means that the collision will decrease. They won't collide as much as the particles in a higher temperature. Make sense? That's why in the cold and the hot, obviously in the hot, you will form more product. Okay? Make sense? Simple. Let's look at the explanation. When the temperature increases, the average kinetic energy of the reacting particle increases. Kinetic energy over here represent movement. Okay? You can say over here when the temperature increases, reacting particle move faster. Alright, you can add that, don't worry. Reacting particle move faster, therefore average kinetic energy of the reacting particle increase. Therefore, number of molecules with kinetic energy equal or higher than activation energy increases. Activation energy is your EA. So every reacting molecule need to achieve activation energy before you change into product. So activation energy, if you remember, also is the minimum kinetic energy required for the reactant to change into product. So if I want to change the reactant to the product, my reactant need to have minimum of this activation energy. But when the temperature is increased, I will have more molecules that have higher kinetic energy. So I will have more molecules that have kinetic energy equal or higher than the activation energy. As a result, effective collision increase and the rate of reaction increase. So temperature, we will talk about kinetic energy and also activation energy. Okay. Last but not least, let's look at catalyst. What is actually catalyst before we start? Alright, you need to know what is actually catalyst. Catalyst is a substance, alright, that you will put into an experiment, that you will put into a reaction. And the purpose that we put this substance, this catalyst into the reaction is to speed up the reaction. Alright, but this substance will not change the reaction. The job is only to speed up the reaction. If you are changing your reactant A to product B, the reaction will remain changing A to B. The reaction won't change, but it will shorten the time. It will speed up the reaction. That is the function of catalyst. Look at the two graphs over here. Both of the graph, I have 5 reactants. This one is without catalyst. This one is added with catalyst. So it's a substance that will speed up the reaction. By how? How can it speed up the reaction? Simple. Provide an alternative pathway with a lower activation energy. So let's see what is actually activation energy. So activation energy is from your reactant to the peak of your graph. This is your activation energy. Alright, so if I have without catalyst, what happened to my reactant is, my reactant need to climb all the way up. My reactant need to climb this stair and all the way up to the peak. Then only it can change into product. Alright? But vice versa, when you have the presence of catalyst, when you add it with catalyst, this is the activation energy. In the other words, my reactant, if I have added catalyst, my reactant only need to climb until here. And I can change into product. So I have 5 reactant over here and I have 5 reactant over here. Without the catalyst, I need to climb so high, so long. Can you see the step? I need to go up so high, then only I can change into product. But with the presence of catalyst, I only need to climb half of the road and I can change into product. So with the added catalyst, I might have all my reactant changes into product. All 5 reactant change into product. But without the catalyst, out of the 5, I might only have 2 of them succeed to become the product. Okay, and another 3 will be in the reactant. Over here, all 5 reactant become product. Can you see over there? Why? Because the amount of staircase that you need to climb, the amount of energy that you need to achieve. With the presence of catalyst, you have an alternative pathway. It's like the highway. Alright, you have a shorter road with a lower activation energy to become product. This is like the shortcut, the highway. But since we have highway over here, alright, and you have a shorter road, so all of the reactant can achieve the activation energy and change into product. So can you see the function of catalyst over here? That is what we call alternative pathway with a lower activation energy. You can see clearly in the graph. Alright, the alternative pathway with a lower activation energy. Makes sense? If you want to use value, the activation energy over here probably is 100 kilojoule per mole. The activation energy over here probably is only 40 kilojoule per mole. So imagine your reactant over here need to achieve 100 kilojoule, then only it can change into product. So your reactant, each and every one of the reactant need to gain 100 kilojoule, then only you can change into product. But over here, your reactant only need to achieve 40 kilojoule. So 100 kilojoule and 40 kilojoule, which one is easier to achieve? 40, right? So all of them can achieve 40. That's why all of them become product. Make sense? Alright, so lower activation energy in the alternative pathway. And that is the function of catalyst. What catalyst does is this. Okay, so let's look at the explanation. When catalyst is added, it will be providing an alternative pathway with a lower activation energy. Therefore, number of molecules with kinetic energy equal or higher than activation energy increases. It's easier to achieve 40 kilojoule than to achieve 100 kilojoule. That's why there will be more molecule will be achieving the activation energy. Number of effective collision increase, as a result rate of reaction increase. So with the presence of catalyst in your reaction, rate of reaction will increase because of the lower activation energy. As a conclusion over here, your concentration can only use for gas and aqueous, and the concentration will talk about number of particles in a fixed volume. Alright, whether it's increased in a fixed volume or decreased in a fixed volume. For pressure and volume, we'll talk only for gas, and for pressure and volume, we'll talk about distance between the particles. We'll talk about whether the reacting particles is moving closer due to the high pressure, or the particles is moving further away because of the low pressure. Okay? And then we move on to your particle size. Particle size only apply to your solid. And for the particle size, the good friend is only one guy. Contact surface area. So we'll talk about contact surface area in the particle size. For the temperature, the good friend of temperature will be kinetic energy. We'll talk about kinetic energy, and also we'll talk about activation energy. Alright, we'll mention about number of molecule that achieve activation energy increase or decrease. Last but not least, in your catalyst. So same thing, like your temperature, catalyst will also talk about activation energy. Alright, where catalyst will be providing an alternative pathway with a lower activation energy. Make sense? That is a very simple summary that I can give to you. So at the end of this video, I hope you understand these 5 factors better. And if this video helps you, don't forget to smash the like button and subscribe to my channel. Feel free to share this video with your friends, and I'll see you in the next video. Thank you and have a good day.